In this video, we're going to learn how to make carbon-carbon bonds by a method called alpha alkylation. And first of all, we're going to talk about the general case, how this happens, and then we're going to talk about three specific types of alpha alkylation in this video and the following ones. So last week we learned that the hydrogen on a carbon that is next to a carbonyl is acidic, much more acidic than we thought it should be because it's a CH, and the hydrogen is attached to a relatively electropositive element, and we normally wouldn't think it'd be acidic, but we've learned now that it's much more acidic, and if we have the appropriate base, we can use the base to deprotonate and form the enolate. And we've learned also that the enolate has two resonance structures, which delocalizes the negative charge over the carbon and the oxygen, making a much weaker conjugate base and consequently then making the original acid a stronger acid than we would have expected. So when we make an enolate, we are ending up putting a negative charge on a carbon and an oxygen, and we'll find out that most of the reactions that will form stable products will be the enolate reacting at the carbon site as opposed to the oxygen site. So enolates you are going to now think of in the future as carbon nucleophiles. Right, we have on the alpha carbon next to the carbonyl, we have a negative charge. So the carbon, we have a carbon nucleophile here. So if we had a carbon electrophile, like an alkyl halide that has a partial positive charge on the carbon and a partial negative charge on the halogen, whatever that might be, chlorine, bromine, iodine, then we can form a new carbon-carbon bond between the carbon nucleophile and the carbon electrophile. So net result is on the alpha carbon here, we have added an alkyl group. Here is our new carbon-carbon bond, and we have done alpha alkylation. We've added an alkyl group onto the alpha position next to the carbonyl. So we're extending the carbon chain in a way where, again, we're using the enolate as the nucleophile and the alkyl halide as the electrophile, forming that new carbon-carbon bond. So there are three general methods by which we can do this. The first is called malonic ester synthesis, the second acetoacetic ester synthesis, and the third direct alkylation. And depending on what products that you want, you will choose one or the other. So the first one is malonic ester synthesis, and so this compound that is drawn here is known as malonic ester. And we will be using ET as an abbreviation for an ethyl group, so we don't have to write CH2, CH3 every single time. So this compound right here is, well, first of all, malonic ester, where does that name come from? Get rid of the ester groups and we have an acid. The 3-carbon dicarboxylic acid you learned was called malonic acid, and so then the ethyl ester of that would be called ethyl, drop the ic acid and add 8, so ethyl malonate, or diethyl malonate, and this is just referred to generically as malonic ester. Okay? So malonic ester forms enolates very easily because the alpha hydrogens here there's two of them, they are next to two carbonyls. And so if we deprotonate and form an enolate here, then not only will that negative charge be spread out over this oxygen, it'll also be spread out over that oxygen. So we'll have 3 resonance structures where that negative charge is spread out, meaning that that would be a weaker conjugate base, and this would be a much stronger original acid. If you remember when we were talking about simple ketones, the pKa of a simple ketone is 19. The pKa of malonic ester is 13. So this is 1,000,000 times, when it's next to, when the CHs are next to 2 carbonyls, it is 1,000,000 times stronger acid than if it's next to just 1 carbonyl. And actually maybe more than that, but roughly about 1,000,000 times. And so if we use a base, a normal, a base that's about the same strength as hydroxide, sodium ethoxide, then that will completely deprotonate the malonic ester. So we have a pKa of 13, pull off the acidic hydrogen, dump the electrons in here on the alpha carbon, and we end up with the conjugate base here that has 1 hydrogen left, a negative charge on the alpha carbon here, and then our ester groups haven't changed. So this is the conjugate base that we form, and then of course it is a really good nucleophile. And then the conjugate acid would be of ethoxide is ethanol, so we are forming ethanol. So that's again how we would abbreviate ethanol. Let's think about the equilibrium involved here. So we're pulling off this acidic hydrogen, we're forming the conjugate acid, and the conjugate acid has a pKa of approximately 18. So we're going from pKa 13 to pKa 18. It's going from stronger to weaker, and so the equilibrium is greatly going to favor the products. How much weaker is this? 10 to the 5th. So 100,000 times weaker acid, and so there is an equilibrium here, but not much of an equilibrium. It greatly favors, and for all practical purposes, it goes 100%, 99.99% to the product here, the enolate. So what we've done by using a compound that is a dicarbonyl compound and one that's very acidic is we have been able to completely convert it to the enolate. So now we have this enolate, we have a nucleophile here, and we can add to it then an alkyl halide. And let's just add a specific one. Let's add bromopropane. And so our nucleophile is going to come and add to our partial positive carbon, the one with the leaving group on it, kick out the leaving group, and we're going to form a new carbon-carbon bond between our nucleophile and our electrophile there. So here's our product of that step. We still have the ester groups on there, and we have this 1 hydrogen still left on there, and then we have added this 3 carbon chain. And so here is our new carbon-carbon bond that we formed. Okay, so we've done that, and in this malonic ester synthesis, I'm just going to walk you through it, and you can see what happens. But once you have added this alkyl group here, then if you add H3O to it, what happens if you add H3O to an ester? Water and an acid catalyst. What happens if you add water and an acid catalyst to any carboxylic acid derivative? It ends up going back to the carboxylic acid. So let's draw the product of that. We have now malonic acid with a 3-carbon chain attached to it. And now a little magic happens. That triangle there means heat. If we heat it, then we do something that is referred to as decarboxylation, and we are removing one of the carboxylic acids as CO2. And our final product here is our alpha carbon, and here is our new bond again to the propyl group that we have added. So we'll talk about this in another video, this decarboxylation. But what you see here in the final product is this. What part came originally from malonic ester? The carboxylic acid and the alpha carbon here. What part came from the electrophile? The alkyl halide, this propyl group right here. And so this is a way to add this fragment to an alkyl halide. So we have learned how to we've learned how to make a carboxylic acid by oxidizing an alcohol. We've learned how to make a carboxylic acid by reacting a Grignard with carbon dioxide and adding 1 carbon. This is a way to add 2 carbons to the chain and make a carboxylic acid. We'll work through a couple examples in the next video.